de WhatsApp.
Sir, asking
Are you able to
Wait, 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 wait.
Okay.
The audio will come there. You can ask him to speak. You can speak.
My problem is this screen is not coming now. When I'm doing a full screen,
But in the screen,
yeah, am I audible? Fine. So we'll start our session. My name is Rohan Nandarkar. I am a PhD scholar from Tufts Lab. This objective of today's objective. I think there is some audio glitch. Okay, am I audible? Right. Give me some feedback. Put headphone on your phone. No? Okay, so we'll continue with our today's discussion on one of the headsets, which was a precursor to the current VR headset which Oculus is providing. So there will be two agendas for today's session. First, we'll understand the hardware provided within the domain of Oculus Rift DK2. It's a developmental kit where we'll be understanding what are the subcomponents involved in manufacturing the DK kit, what are its specification, and ultimately we'll move towards how we can use our phone and calibration method to use it as a 3 degree of freedom VR devices. I believe you would have gone through all the lecture mentioned for degree of freedoms in terms of VR domain as it is concerned. So if we look at a glance, we have it's not coming away. Okay, so here are the specification provided by our VR headset. We have almost so this is some issue with the display, I guess. Okay, we have 1920 cross 1080 panel split. So these are the general specification. I'll go through it and then eventually I'll display you the hardware component and then we'll correlate the hardware along with this specification, which is essential for any VR headset per se concerned. So we have a flat display panel. Right now I'm showing it to you. This is one of the main component of the display. The overall resolution of the screen is 2K screen, that is 1920 cross 1080. You have to split it across left and right, and hence one side of the resolution get divided by two, and we finally get 960 cross 1080 resolution per eye. At the other side, this display comes with a refresh rate of 75 Hertz with a minimum OLED stroke latency of 2 to 3 millisecond. Along with that, there are IMU, which gives you orientation information within the headset, which is sampling at 1000 Hertz. And we have 40 plus IR LED on the DK2 kit and an IR camera to track those IR LEDs. So this is a general overview of the specification is concerned. Let's understand how actually it mints and what is the importance of this stack. So if you see here on the screen, you can appreciate this is the complete hardware. This is a complete DK kit. It has certain critical component which will go through one by one. We have optics. As you can see, there are two eyepieces available. We have an IR camera. In the specification sheet, I mentioned about 40 IR LEDs which stays inside this headpiece. We have connecting cables, adapters. We have IMU and display board inside this component. So we'll go through it on the later slide. So let's talk about optics. As I mentioned in the first row that we have a display with certain resolution and we are going to split those displays into two view, one per eye. We need specific optics and one important parameter related to this optics is interlens distance that is called as IPD. In this particular device, we don't have any variable IPD shifter, whereas when we go through our phones or the latest devices that we have in VR, we can think of having that feature of change in IPD so that we can customize our view. And the whole of this thing is required to perceive basically stereoscopic view because your phone is a single view display. It gives you one view that is plain 2D information. Whereas in the VR, what we require is we require depth perception of the virtual content, and hence this type of apparatus is required. And this is how it started to put optics, and we'll now go to what goes beyond eyepieces. These two eyepieces helps you to visualize what's being projected on the display. Is that slide visible, Madhi? Hmm. So as you can see on the screen, we have a big display as I showed you in the hardware also. Here we have got the display. This display helps us to split our screen into left half and the right half, which is running at 75 Hertz for this particular version of DK kit. And the previous slide, which we mentioned for optics, helps us to visualize virtual content in stereoscopic manner. So that is the objective of this apparatus. They have packed it in such a way so that the said objective is done. But calibration is a key which we'll see in the later go, why it is important and how do we take it forward from there. So the next important thing comes here in picture is the motherboard, like the complete compute unit which it runs on. In those days, they use this particular set of component. This is the HDMI interface bridge, the microcontroller, the IMUs, the constant current regulator for IR devices, the USB hub, and the display. All these things are held together by this motherboard, which was designed by Oculus team. And as I shared that we have a display, on top of that we have an optics. You need to see some virtual content on top of that. So this motherboard helps to visualize, render those information, but still we don't have one critical component right now. How do we orient the virtual content as per the user's perspective? So for that, the next arrangement in this stack comes from the IR lights. We have almost 40 IRs spread across the display headset. Let me show you two components altogether. So as I shared you, this is the motherboard, as you can see here, and this is the gasket along with the IR LED. It may not be visible, but you can refer the images and you can appreciate the presence of 40 IR light at the back of this gasket lid on top of the motherboard. And here comes the interesting part that we need to accommodate for an IR camera. This is external outside in tracking we are talking about. This camera, the IR camera stays from third perspective on the outer perspective. It tracks your headset's IR lights, 14 count as we shared, and gives information back to motherboard about headsets orientation as well as position. All these things happens only when you have calibration mapped. Let's see the complete assembly. All those things, the tracking, the outside in tracking, the rendering of the visual information onto the display, perceiving of those rendered input information, the least latency through optics, and altogether VR application came into existence with this type of apparatus. Now, the question arises, what is that we need if we have to use our phone as a VR headset? That is a frugal method of utilizing your phone, because in recent days, in the current days, we have very good compute power available in our phones. We have very good quality of orientation information rendered from IMUs. So we have a small activity here in this particular slide that we'll be sharing you, or else you can go to xtic.org/projects. There you'll be finding one link to calibration module. That calibration module helps you to understand the complete methodology of calibrating and using your phone as a VR device. One thing on top of that you have to get is, let me show you my phone and then I would be able to make you appreciate that part. We have this phone. It will be a single 2D display. But using that calibration tool, you would be able to visualize a split view in this phone, and you have to put this phone into an optical apparatus, which this Procus provides. Our team will also provide you the Amazon links for the Procus head mount unit. What you have to do is you have to put your phone into this Procus device, follow up the calibration procedure, and at the end of that calibration procedure, you would be able to uh, visualize any virtual content that you will be developing in this course later within the domain of your phone. So let me share you this part. So these are the problem statement and the solution that we are providing with this app. And the instructions are mentioned in that folder. That link which stays with this xtech.org/project takes you to a Google Drive. You can download that calibration suite from the Google Drive, and you can follow the instruction provided in that, so that you can use your uh, laptop and phone as a common unit for calibration and rendering your VR content directly onto your phone. So let me give you a brief overview of the whole process, how it works in that app. So there will be a desktop or a laptop, whatever you prefer to use. You have to run that application. It will open up a local server on your phone on a compatible port. I have hard coded it for 8443 port number. You can customize it as per your port availability. That will lead you to session, which is a two-page session. One is 3d.html and another one is the base page where you can configure all the values. So if you start the server, you have to connect, calibrate, and export the calibration file, which is nothing but a sets of number given in this thing. So this is the reiteration of that process. Let me take you to xtech.org. So this is what I would request all this course members to go. This is xtech.org. You have to click on that part and you have to download this VR calibration suite. When you click on this link, it will take you to a Google Drive. You have to download it. Once you download it, you would be able to appreciate the components, and by following those things, you would be able to download the calibration suite. Mm, is my screen sharing right now?
Rohan, are you sharing anything?
Yes, sir. I'm sharing.
Okay.
Share this. I'm not able to share. Ankur, can you please call Madi? Is it visible?
Not yet.
Okay. I think my session. So I think there was some problem here. Sir, I think I'm not able to share it from my device. Some technical issues there. So it's not allowing me to share.
Can you rejoin this?
Yeah, I rejoined.
That's it. You only give access. Oh, one correct?
Yeah. So is it the browser issues or what?
Rohan, is it on mute?
No.
Can you check now?
Rohan, no. Still not happening.
Okay, Rohan, you have done with the calibration part of it. What else needs to be done?
So I just wanted to share the documentation.
What documentation? Can you no, can you share it through email?
Yes, sir. I will share it through email.
Okay, so let me take over then now.
Understood, sir.
Okay, all right. Thank you, Rohan.
Thank you, sir.
So now let us switch the gears. I'm just wondering whether my video also can be switched on. Yes. Yes. Visible. Okay. Now let us switch the gears. I'm going to now talk about some of the recent advancement in the recent now years on the topics that you have been learning in the course now for the past few weeks, right? There are a lot of recent updates we would like to talk, but one thing which is very now relevant that the topics that you are learning right now is the no the
This is blank basically.
oh yeah, I'm going to share the screen. I'm going to share the screen. Let me share the screen. This is screens, the entire screen. Desktop 2, desktop 1. Is the screen visible? Is the screen visible? Is it visible?
Not to us, sir.
Not? Okay. Let me stop sharing and then let me share it again. Is it visible now?
Not visible to us, sir. There are some blank lines here.
Blank lines again. Okay. Stop here. So, why is that it's not sharing? This is should be sharing. Screens. I choose an entire screen. Yes. Application window. Which application window? Tablet now. Application window. I should be able to share it. This is what I'm sharing.
No, sir, still the same. It's
Same, is it?
yes.
You know what the issue is? Um, okay. Your screen is shared now, but it is not. Why is that it is not shared? I don't know.
I think, sir, it is because of extension.
Let me log out and log in again if it is going to helpful. Give me a few moments. I'm going to log out. NPTEL admin sharing is not turned on. It says, can you now permit the sharing?
Yes, sir, we are processing that. Sir.
1 minute, sir. I'm going.
One.
So given the access.
Thank you. Now let me see.
No, sir, it's still the same lines.
This is still the same.
Your video is also not visible, sir.
Yeah. Mhm. Oh, what is the issue? I think last time, sorry, it's this issue. Video is fine, but only this is an issue.
Sir, we can attempt on resolving through our switch that we have.
Okay.
Muted. Sir, can you send the slides to Rohan?
Can Rohan share the slides?
Yes,
Yes,
sir.
sir.
I can send it to him.
I thought now you also have the same issue.
Yes, sir. Sir.
I'll send it by email or what?
Yes, sir. Email is fine.
Email, I'm sending it right away. Program. I have sent a PPT called Programmable Reality. Can you see whether you have received in your Gmail? Yes, ma'am.
Not received, sir.
Yeah, check again. You must have received now.
You share it, yeah?
He's not, professor is not able to
From his PC.
Yeah.
Rowan, can you log in?
Sir, still not received.
Must have come now. Please check.
Sir, mobile.
Should I send it to another email?
Can you send it to me, sir? Madhi, yes.
Madhi, is it? Okay.
And Ravi, sir, also.
Okay. Madhi, I'm sharing it right away. Take it. Madhi, I sent it to you.
Sir, is the slides visible?
Yeah, it is.
Visible only.
It's perfect, yeah. Thank you, sir.
Yes, can you go into the presentation mode, please?
Yes, sir, we're already at the presentation mode, sir.
Presentation mode, is it? Okay.
As you say, we the pages, sir.
All right then. So can you move to the second slide?
1 minute, 1 minute. So this is wrong. This is wrong. Wait.
1 minute, sir.
Okay.
Yes, sir.
Wait.
Share it, it's not. Yeah, sir, perfect.
Okay. All right. Thank you. So sorry for this hiccup.
Thank you, sir.
I hope now we will make up for the delay. So in the last few classes, few weeks, you've been learning about the 3D modeling and now transformations and now visual perceptions, right? Visual understanding of the entire thing, right? There is a very recent approach now which is happening, which is not talked about in the previous classes, right? So traditionally, we have been using the polygon meshes for representing 3D models, correct? But no, is that the only way to represent 3D models? Right? There are disadvantages of going with the polygon models. Right? So what are the disadvantages and what are the new methods is what we are going to see in the next couple of minutes. Right? So particularly now in the traditional methods, we design polygon meshes and then add textures and then add lighting and then manual modeling. All those things is happening. But in the recent approach, we are living in a AI era. There, the neural fields are used for now the 3D modeling. Particularly, we are talking about two different models. It is called neural radiance fields and 3D Gaussian splatting. These are the two recent advances that we are going to talk about it. And then AI-based reconstruction in general, right? So from manually modeled geometry to data-driven photorealistic scene representation is a new approach which is coming up. We will look at the details of it. Great. Next slide, please. So before I talk about the what is the AI-based models, representation of the 3D geometry, I wanted to give you an idea about there are two different ways to model the 3D models. One is the implicit model, another one is the explicit model. I'm going to tell you that whatever we have been doing is called the explicit models. All the polygon-based models, they are all explicit models. Why is that explicit? Explicitly, a polygon is then ordered to it, right? So again, there is another terminology you will come across. It is called Eulerian or Lagrangian, right? Eulerian approaches to the 3D modeling is called the looking at now each vertexes or each polygon, how it is moving, how it is velocity, and all those things, right? Whereas Eulerian approach is you divide the entire 3D space into into cells, right? Fixed cells. The cell is not moving. Whereas in the Lagrangian model, the cell is actually moving. The particle is actually moving. The triangle is actually moving. Whereas in the Eulerian approach, now the grid is fixed, and then each grid we are looking at what is entering, what is going out, right? So here we call this as a now the Eulerian approach as the implicit approach, whereas the Lagrangian approach is the explicit approach. Next slide, please. This is also called the another way of looking at the same thing. Whether implicit or explicit or Eulerian or Lagrangian, there is another terminologies you will come across in all this recent works is these discrete or continuous. Okay, the polygon models are discrete because we are looking at the vertex assignment only at the discrete points. It is not continuously we are actually representing it. Whereas the other continuous models, a mathematical implicit function is actually defined. And therefore, any point we should be able to calculate and define the function. There is a continuous function, correct? So in the general form is that given a point in the space of 3D point, let us say XYZ, the function will return the property of that particular 3D object. That's a continuous function. Okay, so what are the properties that we can get it? It could be density, it could be color, it could be distance to surface or radiance. That's a light transport. All these things can be inquired from this particular function. That's a mathematical function. This is a nice implicit function. That's a continuous function, right? So all those recent advances is actually, particularly we are talking about the neural implicit function that is called the nerve. We are going to talk about radiance function is a nice continuous implicit field. So what happens is, take a neural network and then give input as a 3D coordinate XYZ, and then output of this neural network you map it to this properties, that is the density, color, distance, and radiance, right? Now you train this neural network to a given input, particularly output. This training, once it is training done, we can ask query the neural network for any combination of XYZ, and then we can get the properties of as the output. So that is why it is called the continuous function, and this is called the neural implicit field. Next slide, please. So then also is called the signed distance function. Now again, we can talk about a function that returning the distance from any point to the nearest surface, right? Either the positive surface or negative, which is if a point is outside the surface, then it is positive. If the point is inside the surface, it is negative. If it is a 0, it is actually exactly on the surface. So this is again can be considered as a implicit representation of the object, right? So like the different properties, color and density, distance also can be another form of query that we can be done. it's for the smooth surfaces. Next slide, please. So the advantages of all this implicit continuous function is that we can have a infinite resolution possible. It is highly, memory efficient. You'll have to just store the weights of the neural network, right? Learnable via gradient descent, which is very, very easy. Next slide, please. There are disadvantages as well. The disadvantages is that to train the neural network, it takes a lot of time, takes a lot of hardware resources, which is not correct, right? That is the radiance field what we talked about, continuous implicit radiance field, right? There is also another thing called 3D Gaussian splatting, which is again, it is it is a discrete, but it is implicit. Okay, it is implicit, but it is discrete. Whereas NERF is the implicit but continuous, right? So in the Gaussian field, what is happening is that 5D input is given to the neural network. Yeah, the 5D input is position plus direction of looking at it, right? And the output of this neural network or the neural system is that it gives you the RGB and the color density, color plus density, right? So it is basically each point is assigned a color and the density depending upon the direction in which now we are actually looking at it. This is what the 3D Gaussian splatting is. It is also called 3D GS. We'll be very often referring to this particular terminologies often. So I would like you to be familiar with that. Next slide, please. So if you can compare these two things, NERF and the 3D GS, right? NERF uses the implicit neural representations, whereas 3D GS uses explicit primitives. So multi-layer perceptron networks for every single ray of light to calculate the color and density in the NERF. So here 3D Gaussian points in the space stores the position, scaling, and rotating, and opacity and color directly. Takes hours. The NERF takes hours to train, whereas 3D GS is much more efficient compared to the NERF. So in the NERF, it is very difficult to edit, whereas 3D GS, it is very, very easy to edit. Is the advantages of the 3D GS. Correct. Next slide, please. So so 3D Gaussian splatting is becoming very, very popular among the virtual reality community and the computer vision community and the media and entertainment community as well, right? So digital twins are being built with 3D Gaussian splatting. Robotics are more and more using 3D navigation is using the 3D Gaussian splatting. Virtual tourism is becoming because the photograph is used for building the Gaussian splatting. Because photographs are used, the representation or model is very, very realistic. And therefore, the realism of the rendering becomes extremely good. And that is what making it very, very popular. Next slide, please. Next slide. Yes. So you could see the shift between the from the polygon models to the 3D Gaussians, from the explicit representations to implicit representation. Okay. Next slide, please. From the very rough polygon models to photorealistic rendering, right? So from the digital shadows to digital models, photorealistic digital models. Next slide, please. From the meshes to 3D GS, right? There are advantages of 3D GS compared to the existing mesh-based representation, which you are all learning, right? the pragmatic quality can be very good for meshes, but 3D-GS it can be little less. Realism can be extremely very good for 3D-GS, whereas mesh can be little less. Cyber sickness triggers can be blurry for 3D-GS. Locomotion confined spaces may be possible over here. Development architectures are unidirectional IoT flow and all possible, whereas in the 3D-GS independent static scene. As of now, we are looking totally static scenes in the 3D-GS, not the dynamic scenes. Whereas meshes, so the pipeline is very, very well known. All these animations and gaming, all using the mesh based. So the traditional pipeline is it's smooth and flow, but 3D-GS is just being built. It is evolving, highly evolving. Next slide, please. Dynamic and articulated geometry is being considered for 3D-GS, and it is evolving. As of now, it is under development. Next slide, please. Semantic geometry is also being considered for 3D-GS. For the mesh-based, it may be easier, but in the 3D-GS, it is still a challenge. It is going to be taking some time. Next slide, please. So spatial computing, it will take some time to get the relation between the two objects in the space. And then therefore, intelligence has to be built on between these two objects. In the mesh-based computing, it may be easier because we know the relation between the meshes. But in the 3D-GS, that kind of spatial computing is still not there, right? The entire field is now evolving. With a given photorealistic was a major advantage. That's what is most attractive as far as the 3D-GS is concerned. Therefore, all the spatial intelligence is being added to the 3D-GS, and therefore now a lot of research is being done and in 3D-GS as of now. If you go to any of these VR conferences, you will see a lot of 3D-GS related activities. Next slide, please. So it is being now standardized. There are a lot of open source tools are there. We will, as part of this course, you will get to use some of the open source tools. Particularly, I'm going to talk about the Open USD. Yeah, Open USD that has introduced the schema for Gaussian splatting data, and WebAssembly is using the unified space as scene description. USD is a unified scene description that is being brought to the industry standards. So this is all for better interoperability, easier web delivery, reduced dependence on the proprietary formats, and all as such advantages, without giving the photorealistic importance or advantages. Next slide, please. So in the coming days, OpenUSD, Open Unified Scene Description, and will be very, very standard. I would like you to be familiar. Maybe we'll give you an assignment on this so that it becomes very, very standard. So applications are in many fields. Next slide, please. So once with the OpenUSD is done, then 3D-GS as we can move towards the generative component of it, right? So as of now, text to 3D models is already existing. So video to 3D world is already existing. Image to 3D models, as maybe it is slowly coming up. In the next few years, you will see a lot of developments in this particular generative, what do you call intelligence or generative 3D, correct? So there's 3D-GS also. You will see now going into the generative 3D-GS, which is not there. No, there are a few researchers are working on it. You will eventually see some generative 3D-GS as well. Next slide, please. So while you see a lot of AI-generated 3D models, right? AI-generated 3D-GS is yet to come, but you will see now coming days. Next slide, please. you can see that AV generated, 3D generated, AI generated 3D model based movies are coming up. Right? So the earlier there was a lot of time taken to make a Hollywood animation movie. Now it is actually reduced, so maybe months, right? That is because of this huge advantage of this AI generated models, right? So from the asset generation to animation and final storytelling, everything is automated now, correct? So including the UI interactions, right? So it's all becoming automated. But that's where the AI is becoming a now biggest advantage, and that is accelerating the development of it. You will see that now the photorealistic content such as the 3D GS also, there is a nice pipeline is being built now, something similar to the already existing now pipeline for the polygons. Next slide, please. So all these things will lead to now very standard open source models. For example, now Trellis point 2 is a very nice Microsoft product which is giving you converting any image into 3D models. And similarly, Modly is another software. You will it's already open source, and you will see that now it is converting any input to the 3D models. You can straight away start using it. Next slide, please. So just like the 3D models, then we'll have to work on the human interactions. Geometry is needed for the human interaction. With the 3D GS, how will the human will be interacting? That is a research topic which is going to come. And some of you can be interested in doing this. Next slide, please. So the pipeline for polygon is very well established, but pipeline for 3D GS is yet to come. And this pipeline is being built, and in the coming days, you will be involved in defining this pipeline sometime. Next slide, please. Okay, there are major bottlenecks, right, in the 3D GS, right? So it takes enormous amount of computation power to build the 3D GS. Static scene itself. Now making it the dynamic scene, it is a feature, not even pass off. Now, there's a particularly some problem called ghost town problem, right? The Gaussian splats, once it is incorporated, there may be some visual ghost, lacking collision and mass or physical deformations. The polygons can we can add physics properties to the polygons, but in the 3D GS, it's all point clouds. There is no geometry attached to it. Therefore, there is a problem called ghost town, which is letting you to go through these 3D models, that 3D representation, and therefore it is not very intuitive. Next slide, please. That's where the realism versus usability will come into picture. If you want usability, if you want to interact like a physical realism, then you'll have to go back to the polygon. If you want more realism, you'll have to use the 3D GS. Next slide, please. So and also this VR splatting architecture is going to be even more important, even more difficult. 3D GS on a desktop itself is going to take a lot of time. But whereas in the virtual reality, the requirement is going to be much more stringent. You must have seen in our course that we need at least 90 hertz update rate. So within the shorter frame rate, frame time, we need to generate the entire photorealistic 3D GS, which is even more challenging when we bring in the 3D GS to the virtual reality. Next slide, please. Okay, so there are a lot of current challenges. We would expect you to look at one of these challenges and then improve on and then contribute to this particular growing field. Next slide, please. So this is what we call it as the programmable reality, right? So the 3D GS offering the photorealistic advantage, can we add a small polygon over to it so that we can easily edit it? We can actually add a physical properties that is actually being considered by a lot of researchers, and maybe that's also is called physical splat, right? So deformable, is it possible? It's all being explored. It is not at now coming to market, but at least now it is being explored in different labs. Next slide, please. So this will lead to the physics-aware photorealistic virtual reality worlds. That is where the future is. Next slide, please. So based on the 3D GS feature architectures are going to be now defined, right? So we need hybrid approach, polygon as well as the 3D GS, now semantic and dynamic and interoperable 3D scenes is what we wanted, and therefore the future architectures will incorporate all these things. I'm going to stop here. If there is any question, I'll be happy to answer. Thank you. Any questions? If there are no questions, I thank you all. So this video will be recorded and then put it on the NPTEL website, and we will assign some assignments in the coming days based on 3D GS and OpenUSD. That will be useful. Yes. Any project idea which, oh, there is one question from Ankit. Any project? Any project?
Idea which you could suggest.
Yeah, idea which you could suggest. Yes. So we will give you a list of some project ideas from which you can choose. But unfortunately, as a part of the NPTEL course, we will not be evaluating for your grades, but we will encourage you to do hands-on with, we will give you ideas, we can talk to our TAs and as the instructors, and then see how we can help you to have a hands-on experience with all this latest developments. Any other questions? Thank you. So if there are no more questions, we can close the session. And thank you all for attending it. We will inform you for the next live class very shortly in the next 2 weeks. Thank you so much. Have a nice day, nice evening, nice week. Bye.